Okay, so welcome everyone to this new meeting of Ithaca Fest. Our first speaker for today is Urs Schreiber, and he will be talking about geometric orbifold cohomology in singular cohesive infinity topoi.
Yes, thanks a lot for the invitation. I appreciate it. Right, so this is joint work with Hisham Sadi that we're doing at New York University in Abu Dhabi, where we're based in the Center for Quantum and Topological Systems. So I hear that there's not all that much time, so let me just jump right in. So I'll start by giving motivation for, sorry, I need to move this bar here. I can't see my own screen because of this. Oh, okay, just a moment. All right, so I'll motivate the three terms, geometric, cohomology, and orbifold before we start. So cohomology, I mean, you might think, okay, this is an ancient thing, but let's just think about it for a second. So in math, of course, cohomology is what allows you to do topology via algebra. That's the topic of algebraic topology. And there's some famous theorems indicated on the right here that have been proven in recent years that prove subtle statements about topology, or rather homotopy theory, by transferring it to the realm of algebra by taking some generalized cohomology of all spaces involved. So that's a big deal in math. In physics, cohomology is actually what encodes what could be called the topology of fields. So you may have heard some of these terms. I'm just throwing them around now. It's not important for the rest of the talk. But there's what's called non-perturbative global phenomena, and it's a big deal in physics. Solitons, instantons, anyons, monopoles, skyrmions. And their fine-grained nature is explained by cohomology. But in fact, in both of these cases, we need to understand the concept in great generality. So cohomology comes with a whole lot of adjectives. I'll just list a few here, maybe the most important one. So there's nonabelian cohomology, there's twisted cohomology, there's equivariant cohomology, and I'll explain what some of these means in the following. There's differential cohomology, there's extraordinary cohomology, that's actually a technical term. There's hypersheaf cohomology, that's also a technical term. And finally, there is global orbifold cohomology. So whenever you want to understand a concept in great generality, that's a paradigmatic case for applying category theory. And in our case, since all this is related to homotopy theory, it's a case for applying higher category theory. So in a sense, we're trying to look for a theory, why category theory? Look for a theory, a good theory of cohomology in this generality. So before we get into the details of what it means, let me just mention an intriguing motivation for those who are interested in connecting math to the real world. So it's kind of striking that generalized orbifold cohomology, which I'll explain in a moment, connects the most abstract math, well, infinity topos theory, as we'll see, to cutting-edge technology. Namely, just throw some buzzwords around. It's not important for what follows, but maybe somebody finds it interesting just to hear this. So it turns out that what is called crystalline quantum materials have very special properties that are actually explained by an extraordinary cohomology theory applied to their space of crystal momenta, Orbi-K cohomology. So there's something very special going on in these materials, which in recent years has been explained only by means of rather generalized notions of cohomology, which is rather striking because this is stuff that can actually be measured, like these cohomology classes can actually be measured in the laboratory. And this goes further with some implications to current developments in quantum computing. But since time is short, let me just jump over that and say a bit about what is an orbifold. I've mentioned the term a few times already, so let's briefly get an idea for what these are. So manifolds are spaces that are locally modeled on Cartesian spaces, RNs, or diffeomorphically to open disks. This is meant to be an open disk here, a local chart of a manifold. Now, for an orbifold, as the term indicates, referring to orbits of a group action, we're talking about spaces that are locally modeled, not on these disks themselves necessarily, but on their quotients by group actions. So in this cartoon, I'm sketching just the most simple situation where you can think of on this open disk, Z-mod 2 acts by 180 degrees rotations. So as we identify points going around, we turn this little disk into this cone thing with a singular, pointy point here, which is not allowed in a usual manifold. And in an orbifold, we allow such things to be local models. So an orbifold is allowed to locally look like this and then glue together along the smooth boundaries. So more precisely, we're talking about finite group actions here by diffeomorphisms. So now to put on our category theory hats, so we've just learned that orbifolds are, maybe in quotation marks, smooth manifolds with identifications of points. But what is this? If you're a category theorist, well, that is just a moment, that is a Lie groupoid, right? It's a smooth manifold of points where pairs of points are identified via, smoothly by families of identifications. These are the morphisms in our Lie groupoid. So in the modern picture, this is not the original definition of orbifolds, but it's well standard now. Orbifolds are actually a special Lie groupoid, smooth groupoids. Specifically they're étale groupoids. So there's some conditions that make a Lie groupoid be an orbifold. And if we regard these groupoids, up to what's sometimes called Morita equivalence, so if we regard the kind of natural notion of equivalence between groupoids, then we think of them, or then the technical term for Lie groupoids in that incarnation is smooth stacks. And I guess I'll be switching between these two terminologies back and forth as we go. So that's orbifolds for us. And now just to give some examples, so good orbifolds, that's actually a technical term. Good orbifolds, sorry, I need to keep removing stuff that obscures my view. Good orbifolds are, by definition, discrete quotients of manifolds. So here's one example, the so-called pillowcase. If you start with a torus, the two-dimensional torus, think of it as being itself already the quotient of R2, then there is a natural involution action on it, which reverses the sign of the vectors in R2. And as we quotient that out, a little thinking reveals that this torus looks actually like, topologically like a sphere, but it has these 4 pointy tips here, which are the 4 fixed points under this action. So we get a space that is pointed in this way. So that's a good picture to keep in mind for a basic orbifold. Of course, this construction works more generally. We can take any Tn, any n-dimensional torus, and quotient out sort of the same Z-mod 2 action that inverts the signs. In dimension 4, this is famous. It's hard to visualize because it's 4-dimensional, but it's famous as the Kummer surface. And this is from an AMS review of the Kummer surface somebody produced with some computer algebra, 2-dimensional projections of this 4-dimensional orbifold. It's not so important what we actually see here, but I think these pictures give a good intuitive impression of what orbifolds look like. You see they're smooth, sort of in the interior, but then they have these very funny singular points. So that's the topic of orbifolds. And where do they arise? Maybe I should skip over this because we do not have that much time. So they arise in math and physics. They have interest. And let's look at what is geometric cohomology. What do I mean by geometric cohomology? So, ordinarily, when you get introduced to ordinary cohomology, the first thing you prove is that it's actually an invariant just of the homotopy type of your base space. It doesn't see any geometry. It doesn't even see the topology. It just sees its homotopy type. So by geometric cohomology, we mean actually refinements of cohomology that are sensitive to more information than just the homotopy type. The geometry of, in our case, orbifolds. So by this, I mean primarily differential geometry, which is what will concern us today, but more generally, one can make cohomology depend on Riemannian and Cartan geometry and G structures. So geometric cohomology is sensitive to differential form data, not just to equivalence classes, not just to Dirac classes of differential forms. And this has deep relevance for these physics applications that I mentioned at the beginning. Here's a picture from actual physics model of a crystal where differential cohomology actually plays a role. I'm not going to explain this now because time is short, but the point is there's high value, if you will, in going for geometric orbifold cohomology. There's actual real-world questions that have answers in this context. So we want to understand that. So we desire a geometric Orbi cohomology in quite some generality, but a general picture of that had actually remained elusive. There had been fragmentary progress on scattered aspects, but no clear global idea. So the paradigm that I'm going to follow here in looking for a good theory of generalized, very generalized geometric Orbi cohomology is the following. Kind of claiming or declaring that actually any flavor of cohomology is mapping classes in a type of infinity topoi. So infinity topoi in this context here, you should think of as being a geometric, possibly geometric homotopy theory, like the homotopy theory of spaces, but possibly with extra geometric structure on them. So the way this works is that we kind of declare, and I'll give a bunch of examples in just a moment of how this works, that any cohomology H, the standard symbol for cohomology, of something with coefficients in something is actually nothing but, it's just, in the sense of category theory, it's just connected components of Hom spaces. So this is like a Hom set and a category, only that set is now a homotopy type between these objects. So that's why my infinity topos will always be called, or the main ones will be called boldface H, because I think of them as actually being a rich enrichment of the little h, or the not boldface H, that is the cohomology theory it expresses. So for instance, what got me started on this topic some years ago with my thesis, as you may have seen, as differential cohomology one can show is mapping classes in cohesive infinity topoi. And I'm going to say what cohesive means. It's infinity topoi that have a geometric structure that satisfies some minimum assumptions that you would want a geometric homotopy theory to satisfy if it expresses anything like differential topology. And our claim, or the claim that I want to be presenting today, or that I want to invite you to, maybe I won't have time to really say much about it, I guess, is that geometric Orbifold cohomology is actually the intrinsic cohomology of what I'm going to call singular cohesive infinity topoi. So these are the things I will explain, but this is kind of the claim I'm making here, we're making. So this has been laid out in these two monographs that are now just going into print, equivariant principal infinity bundles, and maybe appearing next year, geometric Orbifold cohomology. And you can find the manuscripts online as indicated here. So these are the texts from which I'm drawing here. So all details can be explained there. So let's take a step back and now explain some things actually. So what do I mean by saying that cohomology is really about mapping classes? So let's look at some standard examples. So if you have a domain space X and another topological space to play the role of a classifying space, then one generally says that the first, so I'm going to write this H1 of X, so it's the first nonabelian cohomology of X with coefficients actually in the loop group, loop infinity group as it were, of A. And we'll define this, and I'll give examples in a moment. What I mean here, you see this subsumes many things that you know very well. By this I just mean connected components of a space of maps, usual mapping space, compact open topology, if these are nice enough spaces, from X to A. So it's just homotopy class of maps from X to A. So here's examples. So if G is a topological group, then there's famously a classifying space of it, BG, which classifies the G principal bundles. Well, and I just said it, that means that the classes of maps from X to BG are in bijection with, under some mild assumptions, with G principal bundles over X. And this set is also called the ordinary non-abelian cohomology of X. Non-abelian because that group is not assumed to be abelian here. That's why the cohomology theory is non-abelian. And as a consequence, this cohomology set is not itself in general a group, unless G is abelian. If G is abelian, though, we can actually iterate this process. If G is A and hence abelian, then actually BA, the classifying space, is itself an abelian topological group and can be de-looped again. So then there is, in fact, for any n, a space BNA, the n-fold classifying space of the abelian group A. And if we homo to that, so this is funny notation, like my notation for what otherwise you might know as a KNA, an Eilenberg-MacLane space in degree n with group A. So these things classify ordinary abelian cohomology, which you may know as singular cohomology or cellular cohomology or Czech cohomology with nice enough situations. So this is the ordinary cohomology that you learn in, where does one learn it, in school or somewhere? So it's classified, it has these classifying spaces. This is a standard result, but maybe not always simplified as much. Now we can keep playing this game if our space A is a space that is part of a spectrum of spaces. So it's an infinite loop space, if you will. Then homoing to that is called making an extraordinary abelian cohomology theory, or sometimes Whitehead generalized abelian cohomology theory. So this subsumes things like K theory, elliptic cohomology, cobordism cohomology, Morava K theory, and things like that. But there is even more general cohomology than this, often called generalized, but abelian cohomology. Namely, we can just take A to be any space. So if you want to apply this formula, we assume it maybe to be connected, but even that is not so important up to a notation. So we can actually regard maps into any space as being an extraordinary non-abelian cohomology theory. So that perspective has gained some traction in recent years when people were talking about non-abelian Poincare duality, where they were looking for the homology dual of this thing. And we've used it a lot. That's why I'm talking about it. We've used it a lot in theoretical physics. But I just want to amplify that, fancy as it may sound, this is actually an example of this. Is actually one of the oldest cohomology theories that have ever been considered, if maybe not under the name of a cohomology theory. Namely, if if we just take A to be a sphere, which is, in a way, the most simple space that you can choose if we're talking about homotopy types, it's a cell complex consisting of a single cell, then this cohomology theory that is classified by the sphere is actually ancient. It's called cohomotopy because we are mapping into a sphere instead of out of a sphere. A sphere is suited for homotopy, and it has been people started discussing this in the 1930s. So in a way, it's the most ancient maybe cohomology that we have. Okay, so this gives us some idea of kind of basic plane cohomology. So what is twisted cohomology? We're going to speak about twisting a lot. Well, twisted cohomology is if we don't just directly map into our space A, but if we say, well, A might vary in a fibration over our base space X, and we take local sections of that fibration. So that's the same as saying we have a classifying fibration E over some classifying space B gamma, whose fibers are A, and we're fixing a twist, which is the map that classifies our twisting bundle, if you wish. And now the maps that we're talking about are no longer just maps directly to A, but maps into this classifying thing here. So this I'm going to call, or this is usually called H tau for twisted. This is the twist cohomology with coefficients in A, because we're still, this fibration is locally trivial. So locally we're homing into A, but globally there may be a twist. So this is now again a space of maps, but it's a slice mapping space. It's the space of maps over B gamma, if you will. Then we're going to be speaking about equivariant cohomology a lot. This is where these orbifolds, come in, who are locally look like spaces with a G action. So if you have a space, topological spaces that are equipped with G actions, indicated here by Gx on X and Gx on A, then we can look at the equivariant maps between them. And the connected components of the mapping space, the subspace of equivariant maps, that is known as the proper, sometimes, or genuine equivariant cohomology of X, to be distinguished from a weaker version, which is called Borel equivariance. So this is the equivariant cohomology of X with coefficients now in our G space. So you see the point here is I'm just highlighting that concepts which when you open the textbooks, you may not always see presented as being just about maps. These definitions of these cohomology theories are really just about maps. We're always just mapping the domain space into a coefficient space and taking classes of these things. What is then geometric cohomology? What if we want to see more than just a homotopy type of our domain space? Well, that's where the toposes come in. So just as an ordinary topos, so that's my explanation of infinity toposes now. Just as an ordinary Grothendieck topos can be understood as being a category of sets that are equipped with some geometric structure in the sense of geometric logic, if you will. So an infinity topos can be understood as being like a category of homotopy types of spaces, but regarded up to weak homotopy equivalents, again, equipped with a kind of geometry. So then we're going to say, well, okay, if there's just any object in such an infinite topos, now not usually called a classifying space, even though you could still call it that, but often called a classifying infinity stack, mostly for historical reasons. It's really an horrible name in a way, but it's the standard name now. So we can map into that and say connected components of, this is, remember, our home space in that infinite topos. So it's the space of maps and homotopies between maps as morphisms and higher homotopies as higher morphisms. We take connected components of that and just declare that this is our geometric cohomology of X with coefficients in this infinity stack. Again, there's basic examples here. It may sound abstract, but it's actually, it readily reduces to things you know. So if A is now, it used to be an abelian group, remember, if it's now a sheaf of abelian group on whatever side we have as a site of definition for infinity topos, then we can form again a delooping now internal to this topos. That's why I'm giving it now boldface notation, and get a delooped version of our sheaf of abelian groups, called, if it's delooped once, it's called a gerp. If it's delooped twice, called a two gerp, and so forth. But there's lots of historical terminology here, but it's really just shifting up this guy A in degree, and then homing into it under this definition just gives us the ordinary abelian sheaf cohomology in that degree on whatever our space X here is now itself regarded in this eminent infinity topos. So ordinary sheaf cohomology is in here, but also what's sometimes called hyper abelian sheaf cohomology. This doesn't have to be just a single abelian group. It can be a chain complex of groups. Then there's, of course, another operation often called H, or the Dold-Kahn construction, that takes this chain complex of abelian groups and regards it as a homotopy type, if you wish. So this is now a sheaf of homotopy types. As such, we can hom into it That's called the hyper-abelian sheaf cohomology. For instance, the lean cohomology is an example of these things, and many other things. Again, we can just say, well, okay, these are special cases, but we can just really, right, we have all the nice properties of these assignments here actually for any A. So we can just allow any A as a coefficient, any infinity stack, and this might then be called the extraordinary non-abelian geometric cohomology. And again, this sounds fancy, but it's actually there's actually very standard examples. The notation may look a bit wild now, but what this is just saying, suppose we're in a smooth context, suppose we have a sheaf of differential forms. So that's standard notation. If you've ever seen differential geometry of one form, sheaf of one forms with coefficients in some Lie algebra G, there's a canonical action of a Lie group G on that by its adjoint action. So we can form this homotopy quotient in an infinity topos that knows not just about homotopy quotient, but also about this differential geometry here. And then regarding this as our coefficient object for cohomology theory, the cohomology theory we're dealing with is actually a differential refinement of the non-abelian cohomology theory H1 coefficient in G that we've already seen. So this extra factor here, or this extra piece, actually brings in principal connections on these principal bundles that are classified by the underlying non-abelian cohomology. So that's the lightning introduction to geometric cohomology, right? So the punchline here is going geometric means to go to non-trivial toposes. Slicing means to go to twisted cohomology, and so forth. So now we want to put these things into a larger perspective. We want to combine all this. We want to be speaking about twisted and generalized and geometric cohomology, and then see how it globalizes to orbifolds. So the first step to do is we need to pass to a really nice, or technical term would be convenient category of spaces in order to kind of import everything we've just said into a more general concept. And that category of convenient category of spaces is my friend smooth infinity groupoids, as I call it. So it's the analog of the sheaf topos on the side of Cartesian spaces. What do I mean by that? So by the side of Cartesian spaces, I mean this very small subcategory here, cart space, the full subcategory of the category of smooth manifolds, whose objects are just the Cartesian spaces Rn, and so the morphisms are just smooth maps between Rn's, possibly between different dimensions. So this is naturally a site under, or it carries a Grothendieck pre-topology, a coverage by the usual open covers, and we can form sheaf topos over it. That sheaf topos, its objects have the interpretation of being generalized smooth sets. So inside there we find smooth manifolds, but also more general things like, for instance, general mapping spaces between smooth manifolds. And now we're turning this up one notch even and look at the infinity topos over the side. So then we're looking at things. Let's actually say what we're looking at. So an object in here, a boldface X, is now a space that has both a geometric aspect and a homotopy theoretic aspect to it. And we probe that, or the way this space comes to us is that it tells us how to look at little probes of our Rn's in this. So being a sheaf on this side means that it assigns to each object in the side some ordinary infinity groupoid. So a set of maps from this Rn into the would-be X with gauge transformations as morphisms between them, and higher gauge transformations and so forth as higher morphisms. So we assign to every probe space an ordinary infinity groupoid, a set with gauge transformations, if you will. And it's thereby that we understand the structure of this space X as having both geometric structure, and that things depend on how we map our Rn smoothly into it, but also homotopies like our orbifolds will have, where two maps into the orbifold can actually be different and still isomorphic if they differ by one such group action. Okay, so that's this higher topos of smooth infinity groupoids, and that's actually cohesive. So that means, I'll be quick here, that means that the usual geometric morphism it has to the base topos, which is the infinity version of sets, so it's infinity groupoids, has actually a further left adjoint and a further right adjoint. And the point is, from that we can form, as you can see here, we can form the corresponding monads that act just on this topos. And I'll give them these names. So this shape thing will appear a lot in the following. This applies this first left adjoint to get just a bare group, infinity groupoid, and then re-embeds that discretely, geometrically discretely, that is, back into our space. So there's two more here, but let's actually gloss over them because there's not much time. And the point I want to make here is the following, that this infinity top of smooth infinity groupoids is a very convenient, maybe I'd say extremely convenient category in the technical sense of topology, of topological spaces, in the following sense, that topological spaces actually faithfully embed, well, at least once you make them into d-topological spaces, delta generated. So once, if the topology is generated by Euclidean spaces, if you will, which is one standard way of getting an ordinary convenient category of topological spaces, then they actually fully faithfully embed first into the concrete sheaves on Cartesian spaces, then into the sheaves on Cartesian spaces, and then into the infinity sheaves. And the upshot is, why this is useful is that here in smooth infinity groupoids, we are in an actual homotopy theory. We have this operation shape here, and it turns out this shape operation, which is just the operation of applying the shape functor and going back up, that is kind of the ultimate incarnation of the operation of forming path infinity groupoids or homotopy types. So it's well known that if you have an ordinary topological space, you can form a singular simplicial complex, which is a simplicial set, whose vertices are the points in the space, whose edges, whose one cells are continuous paths in the space, and so forth. And that is well known to be a model for what can be called the path infinity groupoid of the space. The infinity groupoid, whose objects are the points, whose morphisms are the paths, and so forth. And it turns out that all these constructions, this corresponding constructions sort of singular simplicial complexes for diffeological spaces, for smooth sets, and so forth, and they're all subsumed under this inclusion, this shape operation. So this shape operation gives a nice context for saying, okay, we have some generalized space, and now we take its ordinary, like non-geometric infinity groupoid of points, paths, and higher paths, and the underlying homotopy type. So in that context, there exist these homotopy quotients. Remember at the very beginning, when I introduced orbifolds, I said they're locally modeled on quotients, and actually I had this symbol here of a homotopy quotient, because then I said we're actually going to think of them as being Lie groupoids, not just plain quotients, but groupoid quotients. So they actually exist here in this infinity topos. So just as a topological space, or if we write our topological space as being the set of points of the space, then we can think of this homotopy quotient here of a topological space by the action, the given action of some group on it by whatever, by homeomorphisms. We can think of this as being the group, or that is the groupoid, actually the topological groupoid, hence the stack, whose, you see my cartoon is indicating the first stage here of, if you will, the simplicial tower of it. So the objects look like they're points in X, but if you have 2 points where one is actually the G translate of another point, then they are connected by, well, for each element G that does this, by a morphism labeled by this element G. And the composition of these morphisms follows the group law of the group that is acting. So these are our homotopy quotients in cartoon version. And an important example of this that will play a big role, if we have enough time, in the following is the homotopy quotients. So the point is the homotopy quotients see much more, as you can see, much more information than the plane quotient. They see, because we remember which G acts, even if G might be fixing this point. In the extreme case where G acts on the singleton space, it fixes everything, and yet in the homotopy quotient, we remember all these elements of G that act on that single point. And so that homotopy quotient is called boldface BG. That's sometimes called the delooping groupoid. It's also the classifying stack for G principal bundles. That's why it's called boldface BG. So these things will play a role. And so now I want to, so this was kind of the review, and now we're going to, maybe there's just enough time for saying this now. I just want to give you the basic idea, the abstract category theoretic idea of what we actually mean when we form twisted orbifold cohomology. I'm going to run you through a diagram now, through some modifications of a diagram. And it's meant to be really simple and elementary, and yet kind of far-reaching. Anyway, so this infinity category of smooth groupoids, smooth infinity group is actually the place to speak about twisted orbifold cohomology, as I'm going to explain now. So in the following, because for just a moment I need a bit more space, I'll write square brackets between or around dashed maps from somewhere to something to mean, we have to, since we're now in a geometric homotopy theoretic context, we have to distinguish between the homotopies that are already built into our objects and those homotopies that are geometric in the sense that they only appear after applying the shape functor. So yeah, maybe I can say more about this just on the next slide. But the square brackets on the following dozen of slides is an abbreviation for saying we take form the mapping space, which actually means now will mean the internal home in our infinite topos, but think of it as being, as before, the topological space of maps from here to there, and from there we take the shape, and then pi 0. Because the thing is, these things will no longer be just topological spaces, so it's no longer the case that, I'll come to that in a moment actually, that it's sort of vacuous to put a shape here, because this thing is in general now itself a stack and not just a space. But anyway, that's what we shall mean now for a moment. We shall mean the shape of the mapping space. So that's an infinity group point. And for the time being, we look at connected components of that. All right, so here we go. So first we call equivalent cohomology. I flashed this very briefly a few minutes ago. If you have a space X domain space with a G action, by homomorphism, and a coefficient space with a G action, then we can look at the equivariant maps between them. So this map, sort of making the collapse diagram here commute, this dashed maps has to respect these G actions. And that was the standard definition of G equivalent cohomology, was the main classes of these equivalent maps between these equivalent spaces. But now that we're in this higher topos where we have access to geometric group points and stacks, it's a simple observation which you can just essentially make by hand, that these equivalent maps actually the same, they're equivalent to maps, all maps, but between the homotopy quotients of our objects. So instead of having the group acting and respect that action, we form the quotient, but the homotopy quotient of that action. That homotopy quotient has a canonical map to BG, because remember, BG was just a point modded by G, so just the map that takes X to the point and sort of mod G to itself, sends every such homotopy quotient canonically to BG. As such, the objects in the slice over BG. And now we can look at slice maps that actually respect these maps to the slice. And it's a simple exercise, but also the first example of an extremely deep fact, that namely homotopy quotient sliced over the classifying space or the looping group out of the thing that acts form equivalently the category of G actions. So these maps actually the same as equivalent maps from X to A. So we have actually reformulated now ordinary equivalent cohomology in this form as being maps of stacks in this form. But this is interesting because it admits a natural generalization now. Since we're seeing, well, we're just mapping in a slice, the slice over BG, we can ask, well, what if we have a richer slice here? So let's suppose we have a topological group gamma on which G also acts by group automorphisms. So this group G, if you really want to be speaking about orbifolds, should be a discrete or finite group. So there's some technical conditions here. Let's assume this is a finite group for our purposes, but gamma is now, as it was previously, a general topological group that classifies our twists, right? Remember how we were talking about twisted cohomology, just for spaces being about maps from X to B gamma, and then having these sections. You see, we have just the same diagram now here, but everything is sliced over G. There's this extra G action here, which itself sits over BG. So then we can say twisted equivalent cohomology is such maps, such slice maps. And if you unwind, and this is part of what this book that we've written unwinds, but this is also fairly standard stuff. What we're really doing here, we're homing into this classifying fibration of gamma principle G equivalent A fiber bundles. And so what this really says, even though it might look a little fancy now, is just the kind of expected statement, the statement you should be expecting, that the twisted equivalent cohomology of X is kind of the classes of sections of an equivalent A fiber bundle over X. But what is important now for us is that actually the G equivariance has now been absorbed into the twisting. If you read this conversely, we started here by saying, well, actually equivalent cohomology itself is already a form of twisted cohomology because it's already incarnated as being about maps in a slice topos once we've passed to our stacks. And now a simple fact of category theory says that kind of if you slice twice, you can just keep the last slicing. So the maps here, the dashed maps that make this full diagram commute, are actually the same as those that just make this top triangle commute, because the rest, I mean, these commuting triangles are already given, so we can just paste with them, and then the top map will also be a map in the slice over BG. So we can actually speak of twisted G-equivalent cohomology by just asking for slices like this. And this is interesting because we're beginning to see that the choice of G is disappearing here. In this diagram, for instance, the fact that this stack here is presented as X modulo G is no longer really important. We could replace this, since this takes place in our category of topological stacks, we could replace this by any equivalent topological stack, and it would change nothing, because changing the homology classes here by anything by equivalence doesn't change things. So we already see a hint here, which is important for orbifolds that are not meant to be defined by this G action, but just presented by it, that things become independent of this presentation. And we can make this more explicit by saying, well, suppose our coefficient bundle is actually pulled back from a universal one. That will actually be the case in applications like for orbifold K theory. That is just always actually the case. Suppose our coefficient bundle here actually itself comes back from pulling back a universal twisting bundle by having a map down here and pulling this back. Well, if that is the case, and so all I'm really saying is, well, suppose this really comes from something that doesn't actually explicitly depend on G anymore, well, then we can form, well, then first of all, we see that our space of maps here is actually the same thing as the space of maps all the way down here to this universal bundle. That's just the universal property of the pullback, kind of having a cone, as you will, if you will, yeah, of this pullback, just the same thing. Sorry, a map into the pullback is just the same thing as having a cone or the original diagram. That's really what's happening here. So if this comes as a pullback, we can just as well look at the maps that go all the way. But for those now, it's interesting, of course, that they're twisted by this map here that also no longer explicitly talks about G. It just goes from our stack all the way to this universal coefficient thing. And so if we just rename our X mod G boldface X as we may, just declare that this is the actual stack class, as a topological stack equivalent to X mod G, which could also be equivalent to X prime mod G prime, so independent now of this presentation. Then the choice of twist at this point, sorry, the choice of G action has actually completely disappeared. We're just asking now for maps from X to this fiber bundle, which lift this given twist here. So this is what we're going to call twisted orbifold cohomology. As you can see, this is actually even more general. I'm not really assuming that X is an actual orbifold. It can at this point be any topological stack or something even wilder. But in particular, this works for orbifolds. So we've found in this way kind of an intrinsic cohomology theory of X that does not rely on presenting X by a presentation as a G quotient. So in conclusion so far, there's a notion of twisted orbifold cohomology, and I'll be quick here now because I want to say something else, which if this would-be orbifold happens to be a manifold, just reduces to ordinary twisted cohomology. And if the X happens to be a global quotient, X mod G, and the twist factors, then it reduces to equivalent cohomology. So we've kind of unified twisted and equivalent cohomology in this way here by this process. And this is a good definition of twisted orbifold cohomology, as long as you don't want to put any geometry into the picture. And this is what people use, for instance, when they speak implicitly, maybe when they speak of things like orbifold K theory. For instance, there's a fibration of the space of Fredholm operators on Hilbert space with some technicality conditions fibered over the classifying space for the projective unitary group. And if you plug that into the previous discussion, you get what's called orbifold K theory. So something that locally looks like ordinary topological K theory, and globally, knows about the equivariance of the orbifold around its singularities. If you put in this other extreme example that I mentioned before, take A to be a sphere, and that universal group that acts on it to be just a rotation of that sphere in its ambient Cartesian space, then we get the twisted orbifold version of this cohomology theory that I mentioned, which is called cohomotopy. And so I have a slide here on how this applies to the solid state physics systems, but I'm not going to speak about this. I hope I have the time now to say, maybe if you just give me 2 more minutes, I want to say how the singular cohesion comes in now. Namely, while all this is nice, this global definition of orbifold cohomology that I presented, we are not done yet. Namely, what we discussed so far are mapping classes formed by concordance. So we formed the shape of the mapping space from X to our coefficient object. But remember, I actually said that a venerable cohomology theory should actually be given by pi 0 of the external home, not the internal home and then take the shape, but the external home, which can also be written as it is the internal home, but then you don't take the shape, but the underlying group of points. So it's not quite in this form yet. The problem is that we're first forming a mapping space here and then applying the shape operation, whereas what we would really want is what in holomorphic in complex analysis is sometimes known as the Oka principle, Oka-Grauer principle. We want to be able to move the shape operation inside. I'll give you examples in a moment, in order to turn our cohomology theory in something that actually looks like this, because it's only in this form that we can actually continue to add more geometry to the picture by applying cohomology operations in the last argument. Okay, so maybe just very briefly. So what is these Oka principles? So here's an example. It's now called the smooth Oka principle. So if X is a smooth manifold and A is any object, any classifying infinity stack, then it turns out that the internal home, the mapping stack from X to A, if you take the shape of that, that's actually naturally equivalent to the mapping stack from the shape of X to the shape of A. So we can take shape inside the mapping space. And the mapping space in that case is actually already in the image of flat anyway. So it's already a plane infinity groupoid. And so this is an important principle for ordinary manifolds. And this has an analog, actually, even though I'm reversing history completely now because this original theorem is older here. There's an equivalent version of a mapping stack version of that, which I'm showing here in a revisionistic form that you can find explained in our book. This is not how it's usually stated. So it turns out the mapping stacks that we're interested in from quotient stacks X to A over BG, we can take the shape inside so we can't actually, not in smooth infinity groupoids, but we can if we have another modality. There's another operator here that kind of remembers the fact that things can have orbisingularities. So this operation, I call it orbisingular operation. And I guess I'm out of time, so I'll just stop with the remark now that we can now build another infinity topos that enhances our cohesive one, which has built in these singularities into its side. And in that infinity topos, this orbisingular operation exists as shown here, and makes these things true and allows you to speak of twisted orbicohomology, and then, even though it starts out live as being a theory of geometric mapping classes, it's actually transformed into what I would call a good infinity topos cohomology theory, where we're really mapping inside an infinity topos between different objects. And yeah, and so forth. And I think I'll stop here, and thanks for it.